So for the last section of Chapter 7, we're going to take a look at improper integrals. So we've talked about the indefinite integral, we've talked about the definite integral. Now what we're going to be looking at is what happens when our bounds may be infinity or negative infinity. So again, we're going to look at the concept of our definite integral to allow for the infinite integrals of integration. And again, we may also have vertical asymptotes within the interval of integration. These will also classify us as an improper integral if between your bounds you have a vertical asymptote. So when this happens, we have what are called infinite discontinuities. We call intervals with infinite intervals of integration or infinite discontinuities within the interval of integration improper integrals. So again, what makes an improper integral? If one of your bounds is positive infinity or negative infinity, or if somewhere between your bounds you end up with a place where the function would be undefined. So here's some examples of improper integrals. So here's an improper integral with the infinite interval of integration. So here's some examples. Notice in the first example, your upper bound is a positive infinity. In the second example, the lower bound is a negative infinity. Or you may also have bounds that are both positive and negative infinity. So we classify them as improper integrals. Improper integral with infinite discontinuities in the intervals of integration. So for example, here's a function where my lower bound is negative 3 and then upper bound is positive 3. However, for 1 over x squared, we know at x equals 0, which is between negative 3 and 3, this would be undefined. So we classify that as an infinite discontinuity and an improper integral. Again, here is an integral from 1 to 2. Notice at my lower bound of x equals 1, this would make the fraction undefined. So we have an improper integral. Again, from 0 to pi for tangent of x, we know at x equals pi over 2, the tangent is undefined. So these are examples of your improper integrals. Improper integrals with an infinite intervals and infinite discontinuities of integration. Again, right here, notice you've got both cases. You've got 0 where it's undefined and the upper bound is positive infinity. And again, your lower bound and upper bound are infinity, but we also know that this fraction would be undefined at x equals positive 3 and negative 3. So sometimes your improper integral may have not only the upper and lower bound with infinity or negative infinity, but it's discontinuous at that particular value between your bounds. So if you consider when you've got an integral in the form going from a lower bound of a to positive infinity, and again it's non-negative, and again we're looking at the area under the curve, basically what you're looking at is the area under the curve. Eventually, if we can find the area under the curve, even though this is going to positive infinity, what's happening is the area becomes so small it becomes insignificant. So what happens is we talk about finding an area of the portion under the curve. So like I said, as b approaches infinity, the portion will eventually be able to fill out over the interval. So for example, if you take a look at the area under the curve from 1 to infinity of 1 over x squared dx, what you're going to do is you're going to rewrite your integral as a limit. So I'm going to just call my upper bound b, and what I'm actually going to do is I'm going to find the limit as b goes to infinity of your integral 1 to b of dx over x squared. So when you have your bounds where it's a positive or negative infinity, we're going to rewrite it because that's what we're doing. We're going to find the limit as you're approaching infinity, if it exists. So when you take a look at this particular problem here, again, you still want to do your properties of integration. We're still going to integrate this, so I have the limit as b goes to infinity. And again, when I integrate 1 over x squared, that's going to give me negative 1 over x. And again, I'm going to evaluate this from 1 to b. So when I plug in my bounds, I have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. So when I plug infinity in for my b, So when I find the limit as -1 over a really, really, really large number, because as b goes to infinity, it's a really large number, well, -1 divided by a really, really, really large number is going to give me a 0, minus -1, which is a +1. So then the area under this curve for this improper integral is just going to be 1. So as we saw from that improper integral, that this has a finite value and is not infinite. So we can actually calculate that area under the curve. So in the case where we found that the limit exists for the improper integral, then we say that the integral is going to converge and that the limit is defined because we can find the value of the integral. In the case where the limit does not exist, because there's going to be cases where we're not going to be able to find the area under the curve, we say that the improper integral is diverged and it does not have a value. So for example, let's take a look at your integral 0 to infinity of x times e to the negative x squared. First of all, you want to rewrite when you have infinity as your upper bound. I'm going to call this upper bound a b. So I'm going to find the limit as b goes to infinity, going from 0 to b, of x times e to the negative x squared dx. And again, I'm going to do a u sub to integrate this. My u is equal to negative x squared. My du is a negative 2x. So I'm going to factor out that -1/2. So I have the limit as b goes to infinity of -1/2 times your integral going from 0 to b of e to the u du. So when I find my integral, I'm going to have the limit as b goes to infinity of -1/2 times e raised to the negative x squared. And again, I'm going to evaluate this from my bounds of 0 to b. So when I plug in my bounds, I have the -1/2. Again, I'm going to find the limit as b goes to infinity of -1/2 times e to the negative b squared minus e to the negative 0 squared. So the limit as b goes to infinity of -1/2. Again, I know this is actually 1 over e to the b squared, and again, as b is approaching infinity, again, when you've got 1 over e to the b squared, 1 divided by a really, really large number is going to 0. Minus e to the 0 is 1. So -1/2 times -1 is +1/2. So we would say that example 1a is going to converge, and it's converging to 1/2. So in the case of the next one, we have my improper integral going from -1 to infinity. Again, I'm going to rewrite this bound with a b. So I'm going to find the limit as b goes to infinity from -1 to b of x over 1 plus x squared dx. Again, this is going to be another u sub. U is equal to 1 plus x squared. My du is a 2x dx. Again, so I am going to have to pull out that 1/2. So when I integrate this, I know it's going to be 1/2 times the natural log of the absolute value of 1 plus x squared. And again, I'm going to evaluate this from b to -1. I'm just going to do this on a separate sheet of paper since I'm getting a little squished here. So again, once I integrate this, I have the limit as b goes to infinity of 1/2 times the natural log of 1 plus x squared. And again, I need to evaluate this from 1 to b. So I plug in my bounds. I have the limit as b goes to infinity of 1/2 times the natural log of 1 plus b squared minus the natural log of 1 plus 1. So if you remember what your graph of the natural log looks like, your natural log graphs have the vertical asymptote at x equals 0. And as your x values are going to infinity, your graph is increasing. It's not approaching a fixed limit. So then, because this part right here is approaching positive infinity, the whole thing is going to diverge. That's because this graph is approaching positive infinity. So if one part diverges, the whole thing is going to diverge. So for example, 1b, we would say that this improper integral diverges. So when you've got the lower bound being negative infinity, we're still going to rewrite. We're going to call the lower bound a, and we're going to rewrite this, the limit as a approaches negative infinity. Again, just like when the upper bound was infinity, the integral is said to converge if the limit exists, and it diverges if it does not. The improper integral of f over the entire interval, so again, if your bounds are both negative infinity to infinity, you have to split your integral somewhere. So if you have a case where both your bounds are infinity and negative infinity, what you have to do is you have to split the integral at a particular value. Does it matter which number we split it at? No. But typically, unless of course there's a place where it's undefined between negative infinity and infinity, but as you know, the easiest number to deal with when you're dealing with bounds is to make that bound equal to 0. So typically we split it at 0. The improper interval, like I said, is said to converge if both terms converge, and diverge if either. So only one of them has to diverge in order for the whole thing to diverge. So for example, let's take a look at the integral of negative infinity to 3 of 1 over x squared plus 9 dx. So again, first of all, I'm going to rewrite my bounds. So since my lower bound is negative infinity, I'm going to rewrite this as the limit as a approaches negative infinity from a to 3 of 1 over. Now, as you know, this is set up to look like your inverse tangent integral, so I'm going to factor out a 9. So that'll give me an x squared over 9 plus 1 dx. I can factor out the 1/9. So I have 1/9 times your integral of going from a to 3. 1 over, I'm going to rewrite x squared over 9 as x over 3 to the second power plus 1 dx. Now when I integrate this, I'm going to have to do a u sub, so u is equal to x over 3. My du is 1/3 dx. So I have to multiply my 1/9 by 3, so that's going to give me a 1/3. So I have 1/3 of my integral going from a to 3 of 1 over u squared plus 1 du. So I have my inverse tangent of x over 3, and again I'm going to evaluate this from a to 3. So again, I want to find the limit as a is going to negative infinity of 1/3. Now I'm going to plug in my upper and lower bounds. So my inverse tangent, when I plug in 3, 3 over 3 is 1, minus, plug in my lower bound, the inverse tangent of a over 3. So 1/3, now the inverse tangent of 1 is going to be pi over 4. Minus, now the limit as a goes to negative infinity of your inverse tangent. So this is where you have to remember what the graph of your inverse tangent is going to look like. If you remember, the inverse tangent has two horizontal asymptotes, one at negative pi over 2 and the other one at pi over 2. So the inverse tangent graph looks something like that. Remember, this 1/3 is just a horizontal stretch or compression. It's not affecting where the asymptotes are. So as you're approaching negative infinity, you're looking on the left-hand side of the graph for inverse tangent. So as you're approaching negative infinity, it's approaching the horizontal asymptote of negative pi over 2. So this is all approaching negative pi over 2. And again, I have to multiply that by my 1/3. So I have 1/3 times pi over 4 plus, this is going to give me a pi over 6. So 1/3 times pi over 4 plus pi over 6. So I know this is going to give me pi over 12 plus, oh, this is just, I'm sorry, it's just going to be negative, it's just going to be negative pi over 2. And this is going to be plus pi over 6. I don't need to multiply by a third, that's just your compression, I'm sorry about that. So this is just approaching my negative pi over 2. So pi over 12 plus pi over 6, so pi over 12 plus 2 pi over 12 is going to give me 3 pi over 12 or pi over 4. So then that's going to converge. So in the case here, where your bounds are both negative infinity and positive infinity, again, I'm going to split. There's no place between negative infinity and infinity where this is going to be undefined. So the easiest place to split this integral is going to be at 0. So I'm going to rewrite this again. I'm going to replace my negative infinity with a. So the limit, as a goes to negative infinity, I'm going to rewrite this from a to 0 of x over the square root of 2 plus x squared dx. I'm going to add that. Now I'm going to replace my upper bound with a b. So again, I split it at 0 from 0 to b of x over the square root of 2 plus x squared. And this is the limit as b is going to infinity, dx. So now, when I go to do my integration, I can do a u sub. U is equal to 2 plus x squared. My du is equal to 2x dx. So I can factor a 1/2 out of this particular integral. So it's going to be the limit as a goes to negative infinity of 1/2. And again, when I integrate by u to the negative 1/2, because that's what I'm going to end up with, u to the negative 1/2, that's going to give me a u to the 1/2. So I end up with 1/2 times 1/2 u to the 1/2 plus the limit as b approaches infinity of 1/4 u to the 1/2. So when I clean this up, what I end up with is I end up with a limit as a approaches negative infinity of 1/4 times the square root of 2 plus x squared. And again, I'm going to have to evaluate this from a to 0. I have to add that to the limit as b approaches infinity of 1/4 times the square root of 2 plus x squared. And again, I'm going to have to evaluate this from 0 to b. So now remember, all it's going to take is for one of these to diverge in order for the whole thing to diverge. If you take a look here at the one where b is going to infinity, the number underneath this square root is getting larger and larger and larger. So this is not approaching a fixed number. So this part right here is going to diverge. Doesn't matter what's happening here. This part's going to infinity. So we say that this whole entire integral is going to diverge. So when you're considering integrals whose integrands have an infinite discontinuity, what's happening there, what we mean by that is you have a place between your bounds or at your bounds where the integral is going to be undefined. So if we have an endpoint where it's undefined, we're going to be looking at the limit slightly to the left. So for example, if we have a vertical asymptote at x equals b, and b is my upper bound, what we're going to do is we're going to calculate the area under the curve as close to b as we can get without being equal to b. So what we'll do is we'll look at a left-hand sided limit. We want to find the limit as k approaches your vertical asymptote from the left and calculate the area under the curve. Just like with the other improper integrals, if the limit exists, we will say that the improper integral converges, and it will diverge if it's not a find a value.